we are going to be looking at finishing off first the calculus of parametric curves, which is kind of nice. I'm going to look at finding second derivatives. And we know how you do that, but I want to do more of them. And finding vertical and horizontal tangent lines. Okay, let's do question 10, which is finding horizontal and vertical tangent lines. So I have got x is e to the sine theta, and I've got y equaling e to the cosine theta. So there's some kind of asymmetry going on here. And if you want to find vertical and horizontal tangent lines, don't you just need to find when is the derivative 0 for horizontal and when is the derivative undefined? If you want vertical, right? Like I said, if you start talking, people come. Well, to find dy by dx using theta as the like the time variable, it's dy by d theta on the top and dx by d theta on the bottom. Hopefully you recognize these as chain rules, right? So what you're going to get is e to the sine theta times the derivative of sine theta, which I'm going to stick at the front as cosine. And this fellow is going to be e to the cosine theta, and the derivative of that is negative sine theta. And of course, theta goes on forever, right? But in this question, we're only interested in finding, well, how do they phrase it? The horizontal tangent with the smallest value and the horizontal tangent with the largest. So in other words, they're going to be looking for two answers for each, right? Because this shape, whatever it is, will repeat itself forever, or it'll cycle on top of itself forever. Depends on what it does. So to get the horizontal ones, we're going to solve when is dy by dx equals 0. Since this is dy by dx, isn't when is it 0? Doesn't that simply become when the numerator is 0? Don't care what the bottom of a fraction is. The bottom of a fraction will never make something 0. Won't it always be the top, right? 0 over 7, 0 over a billion and 7. It's still going to be the 0 on the top. And if you want to solve this, don't make your life difficult. Make your life easy. Won't this be 0 when cosine is 0? Would you agree e to the power of sine theta? Whatever you play in there, isn't it going to be a number that's never 0? Right, so I'm using that. Now that I know that, don't I have lots of possible values for the cosine? But I want well, I want, oops, I almost put the wrong answer in there. I want pi upon 2, I guess, right? And maybe 3 upon 2 pi. Would you agree they'd be two good choices for the cosine being 0? Now, if I want to get the vertical, don't I just solve dy by dx equals undefined? And if you're undefined, doesn't that just translate to the bottom is 0? So we're trying to solve that one. That one being 0, which is, we're trying to solve this one being 0. And would you agree that 0 equals 0 and 0 equals pi would be good examples of that? Now, there are 4 answers there. 2 of them, these two, generate horizontal ones, and 2 of these generate vertical tangent lines. And the way they've phrased it is the smaller y value and the larger. So let's just pick for this guy what we've got. Right, so the x coordinate is going to be e to the sine. So when theta is pi upon 2, the x value is going to be e to the sine of pi upon 2. That's going to be e to the 1, which is e. And when you use theta, it's 3 upon 2 pi. Oh, I forgot the y coordinate. And the y coordinate is going to be e to the cosine of pi upon 2. And the cosine of pi upon 2 is 0. So that's 1. And then at 3 upon 2, you're going to get e to the sine 3 upon 2 pi. That's e to the negative 1. And y is going to be e to the cosine of 3 upon 2 pi, which is still 0, which is just 1. So in this one, you get coordinates E1, and in this one, you get that coordinate. If you're comfortable, then you can figure out which one goes where, and you're done. Oh, and they drew little pretty pictures of it. That's nice of them. What do I need to do? Oh, finding second derivatives. Okay, let me find one more second derivative to play about with. I know that one looks familiar. I think I've done that one. Did I do e to the t and t e to the negative t? Did I do that last Friday? So x was e to the t and y was t e to the negative t. Did I do that one? No, okay. Then we're now going to do an example of finding the second derivative. And it's going to be that guy. And it's going to be that guy. And just to make my life easy, I'll do some of my working here. That's this guy's derivative. Of course, to do this guy, one, I have to do a product draw. I'll call this f, call this g. So it's going to be f dash j plus f of g dashed. So what do I get? I get 1 times e to the negative t plus t times negative 1 e to the negative t, because that's a little baby general. So that's e to the negative t, 1 minus t. Okay, I've got all the pieces in. To find the first derivative, it's just dy by dt on the top and dx by dt on the bottom. And dy by dt is this ugliness, and dx by dt is that guy. And I'm just going to rewrite this thing like that. And just tidying it up. I could have brought that downstairs as well, and that would have worked equally as well. Now, if you want to get the second derivative, it's a much clunkier formula. You differentiate the first derivative with respect to t, and that gets divided by dx by dt. Right, now dx by dt is still this guy, but when you differentiate the top, do you see that this, when you differentiate it with respect to t, is a product draw? So to save time, I'm just going to do the product draw. F dashed is this guy, leave the g alone, plus leave the f alone, and differentiate this guy. And now what you have is e to the negative 2t, because you can pull that out as a common factor. Negative 2 times this guy, negative 2 times this guy with that guy. All over e to the t. and some style points. And we're finished. Are we
Did I
good?
say 26 minus 3, or is that 2t minus 3?
It's 2t. 2t. I'm scanning. Let's finish some guys off. Now let's do a puzzle one. Question 11 says, at what point or points, it might be more than one, on this parametric curve, does the tangent line have a slope of a half? That was a one-off question. I know
Wouldn't you just need to solve for the differential and then see when it equals 1/2?
That's exactly what you need to do, yes. So I think this one's easy to do without getting too caught up on the formula. So dy by dx, let's write that again, it's ugly, that one. Dy by dx is this guy's derivative, which is 3t squared, over this guy's derivative, which is 18t. And if I cancel that down, I get that. Oh, come on, that's too easy. What did I do wrong? Is that as easy as it looks? Okay, then I want that to equal a half. So that's when 2t equals 6, that's when t equals 3. So there's only one solution, and the coordinates of that are when t is 3. And what's that? 81 add 9 is 90. 27 take away 9 is 18. So the only point on that curve that has a slope of a half is at the point 90, 18. Check it. Yeah, okay, it's right. Don't you get worried when the question's too easy? You think, nah, I missed something here, but that question was remarkably clean. Now, areas enclosed by parametric curves. Suppose I have a parametric curve x equals 4 sine theta. Or okay, we'll call it t because this is going to be question 12. And we'll have a y, which is sine t, cosine t. And we're going to do t goes from 0 to pi upon 2. I can handle that. To save time, I'm just using their picture. Can you trust me that that's what the thing looks like when you sketch it in Desmos? Okay. And they want to find the area that this is enclosed with, right, and the x-axis. Even if they never told me the x-axis, I'm pretty sure I know what they want. They want that guy, don't they? So how do you integrate things when they're in parametric form? Well, if you write down an integral, it's that guy. Wouldn't you agree that is this guy? So far, so good. Now, Let's look at this guy. Algebraically, isn't this guy that guy? It's a kind of sort of a related to a U-sub. Only I'm turning things into t's. Now, do you notice it's like the t's cancel out? Now, what does that look like? It looks like y, but you write it down in terms of t. And it's dx by dt, so it's not this guy, but the derivative of this guy, which is 4 cosine t dt. Do you see that we've now got our integral? And doesn't our integral have only t's in it, and it's been integrated with respect to t? There's one little piece of the puzzle missing. Don't we need limits of integration? What do you think those numbers are?
Well, it's going to be wherever we're contacting the x-axis, so it's probably going to be 0 and 2 pi over 2.
And I bet money it's going to be those two. But you could
Do we
double
have to
check
plug
into
the
this.
limits in and change them like we would in a U substitution?
Not really, because they're already converted when you did this. So you have one less thing to worry about. Now I'm going to rearrange this integral quite a bit. It's going to be 4 sine t cos squared t dt. And I'll rewrite it up here because I need room.
Could we use a double integral or a double the trig rules to make the cosine go away?
You could try. I don't think
Double
it would work. You could try, but it wouldn't help. Think U-sub. And by sheer coincidence, that's what my Calc 2 students are doing right now. And we did a question not unlike that one. If you ever see a combination of powers of sines and cosines, a U-sub is a strategy that could easily work.
Then make
But there is
U cosine of t?
correct. I was going to say you have to make sure you pick the right one to be your U-sub. And it's the cosine of t in this case. And if you differentiate with respect to t, you get negative sine t because I'm differentiating. If you do the crossover, you get that. If you divide both sides by negative sine t, you can isolate the dt, and you get that. So we now have the integral of 4 sine t u squared negative 1 over sine t du, which becomes negative 4 u squared du. I'll then do the power rule. Add 1 to the power, divide by the new power. I will then return it back to the cosines. And at this point, I'll do the t equals 0 to t equals pi upon 2. So this will be negative 4/3 the cosine of pi upon 2 cubed, take away negative 4/3 the cosine of 0 cubed. And that guy is nothing, so the whole thing is nothing. And this guy is 1, and 1 cubed is still 1, and negative 4/3 times 1 with another negative ends up being plus 4/3, and the answer we get is 4/3. The key to doing this question is to remember that for me. Because once that is written down, doesn't this just become a Calc 2 question where you're integrating something? In this particular case, it was integrating a trig, but couldn't the next time it be, you know, t cubed plus 5t or something, right? It'll be what it is. You want to see another one? Okay. And this will be our last one, and then we're moving on to a new section. And this one is similar to 13. So x is going to be t squared take away 2t. Y is going to be the square root of t. And they have given us a picture. And evidently it looks like that. And they want to get it, the area where it cuts the y-axis. Which means it's that guy. Now I know how to get the area. I've got my little formula, which I've got here. It's going to be the integral of y times dx by dt dt. And it's going to be this guy. My apologies, it's going to be this guy times the derivative of. Did you know I didn't swear there? Did you
You
see
want
how
to find the derivative or the integral when with in terms of y, because you're not going over the x-axis.
No, it is the parametric is the formula that we use to calculate the area for a parametric curve is this formula, regardless of what direction we're integrating in. At least it's pretty versatile. The mistake I was getting was for some reason I couldn't get my brain around the fact that y is the square root of t and x is 2t take away t. That was the guy that I had a lot of trouble writing down because my brain kept on switching places. Now, do you notice that's the exact same formula, even though in this case it was the y-axis, and in this case up here, x-axis, in this case up here it's the y-axis.
There is a small mistake. It should be 2t minus 2.
Did
Not
you all
2t
catch
minus
that
2.
second mistake? Thank you for catching it. Now, my brain is thinking at this line here, and I wish I hadn't gotten myself distracted. Would you agree that we need to know these two guys? The problem is you might want to know those two guys, but you'll find their y values, not their x values, right? And that's not what we want. Don't we want these to be in terms of what the t is, right? So I want to know what the t value is here. And I want to know what the t value is here. I don't want to know that the x coordinate is 0 because that's directly no use to me. So I'm not going to plug necessarily 0 into that. So if you cross the y-axis, right, isn't your x coordinate going to be 0? So what I'm going to do to find these two t values is that I'm actually going to solve when is the x coordinate 0. And if I pull out a t, I get that. And that means that one of those t values is 0 and the other one is going to be 2. Well, let's check it out. When t equals 0, you get 0. So that one there is definitely the t equals 0. And this one up here is the t equals 2, which means that goes 0 and that goes 2, and we've got it. Are you comfortable about how we got the limits of integration in terms of t? Are we good with that? Right, move on then. It's going to be the integral from 0 to 2. I'm going to call this guy t to the half. Okay, tell me where I go next. I want to integrate this thing with respect to t. What should I do next? And I deliberately turned it into t to the half to kind of give you a clue.
Distribute,
most of
multiply it
that's-
through.
Yeah. So 3 halves, take away 2t to the half dt. And that's where I'm going to stop with my dot, 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 dot thing. Would you agree that's just an ugly power rule? Right, add 1 to the power, divide by the new power. And then won't you plug t equals 0 and t equals 2 and get the answer? Make sure that you get exact values. So it's okay to have square roots of 2 in the answer. In fact, you better have some square roots of 2 or it's not right. And we are finished with that section.
For style points, is it better to have, like, hypothetically, say you had 5 halves of x or whatever, is it better to write that as square root of x to the 5th, or is it better to write that as 5 halves of x?
Try to think of what you said. So you've got t to the 5 halves, right? That's what you said. Yeah. It's style points. That's what the guy could look like, right? Which means it looks like the original, right? Now, if that was part of your calculation, we pretend that I was going to do it at t equals 0 and t equals 2. Let's say that's all I needed to do. It would be the square root of 2 to the 5, take away square root of 9 to the 5. 2 to the 5, however, if you work on it enough, you'll be able to find out that it's 4 root 2, take away nothing. And then it would be 4 root 2. I don't know if that's answering your question, Tim.
Well, the first bit actually answered my question, but the second bit was good too.
Right, because you're going to have to get exact values, right? And you're plugging into, you're going to get 3/5 this guy and 4/9 that guy. It's going to be really ugly, and they're going to be square roots of 2s floating around, I can guarantee it. We are finished. Chapter 10. It's a very baby chapter, because there are only a couple of things in chapter 10 that we really wanted you to get used to. And what was that? I want you to get used to the fact that parametric curves are a helpful way of describing unusual curves in 2D. Right? Later on, we're going to find that parametric curves are how you describe curves in 3 dimensions. So you don't write them down as y equals x cubed anymore. And that's how you would write a curve in 2 dimensions. When you've got 3 dimensions, don't you have an x, y, and a z coordinate system? And so the y equals f of x doesn't work anymore, right? And so that's giving you a little taster of how you can deal with the 3D world when it comes up. And that was a little bit of calculus involved, but that's fine too. So what we're now going to move on to is question 12.1. Or chapter 12.1, I guess. And we're going to look at the 3-dimensional coordinate system. I'm going to give you some notes on this before we delve into anything too specific. And one of the biggest problems that we are going to have is how do you draw 3-dimensional situations on 2-dimensional pieces of paper? Would you agree that's not a very easy process? So we tend to create an X, a Y, essentially the floor, and a Z is height. Would that seem to be a reasonable way of defining X, Y, and now our 3rd dimension, which is Z? Now, when you are looking at a shape or a point in 3D space, it is very difficult, and with the best will in the world, it's very, what's the word I'm looking for? Ugly way to describe it. Here is the first problem. the axes are orientated in a strange way. Have you noticed that the X and the Y are allegedly coming out of the paper? If you wanted to imagine what would this look like, you have to be inside the paper, looking that way. Can you see the X and Y axes now making a little bit more sense? Why they're orientated in that rather strange way. Now, if you go in this direction, won't you be negative X's, in this direction, negative Y's, and down the way? I think vertical's the only one that makes sense, right? There are two reasons for this. The first reason we orientate the axes in this unusual orientation is to make positives come out of the board because they're more likely than negatives. And the second is because of engineers. That's not a joke. I don't even know if any of you know this, but there's a thing called the left-hand rule and there's a thing called the right-hand rule. Yes, Molly did a finger thing. It's these three, isn't it? One's your thumb and then these two guys. And you do things like this all the time. And if you do it a lot, you end up with a sore wrist, right? That thing. This is oriented.
Forget the curl rule.
Yes, the curl rule is part of that, right? Now, to make sure that the orientation of the, oh God, I can't remember now if it's the left or the right. Let's call it the right-hand rule because I can't remember. A 50% chance of telling you the right name. This is orientated so it works with the right-hand rule, right? So that when you do your thing, you know, it'll point the right way. So up will be your thumb and it will point the right way. Okay. For those who have not a clue what I'm talking about, will you just settle for that's the way we draw them, right? And live with it, right? But at least if we orientate it this way, it matches up with the way the physics people see forces and torque, you know, because one torque unscrews a bolt, doesn't it? And the other torque screws it back in, for instance. So you don't want getting those two mixed up, do you? That would not be a good idea for anything that you build. So far, so good. Now, if I want to tell you a point in 3D space on this diagram, I will call it 1, 2, 3. We use coordinate system. And this is not a surprise. Would you agree it makes perfect sense that the first number is the X coordinate, the second number is the Y coordinate, and the third number is the Z coordinate? Does that kind of make sense? So, okay. Now, to draw it, I'm going to try, but after I've done it, I think you'll realize why we don't bother. We don't expect you to draw sketches of points in 3D space. Would you agree? It's just 2D paper ain't up to it. But here it goes. You go 1 in the X. You go 2 in the Y. And then you go 3 in the Z. And that's where P is. Do you see that I'm trying to describe P as floating somewhere outside this piece of paper? And you see how difficult it is to do that unless you put a couple of these little construction lines in, right? These little invisible dotted lines. So far, so good. So we've got 3 coordinate axes, X, Y, and Z. They're orientated in this funny way because engineers want it that way. And if you want to plot a point, you probably shouldn't. But if you did want to plot a point, isn't this the way you would have to try and describe it to someone? Why? Well, suppose I told you, here's the point Q. Can you really tell where Q is? Don't you need a couple of 3 alongs and 2 to the side and 1 up kind of thing, right? You need to see these extra lines. Now, let's talk about what are called the planes. There are some interesting names. There's a guy called the XY plane. And the XY plane is essentially the floor. So the XY plane are all points that lie in the floor. Does that seem reasonable? Now, I'll give you a coordinate of a guy in the XY plane. Here's another guy. And here's the last one. What do you know about the coordinates of all the points who lie on the XY plane?
Z is 0.
No, their Z coordinate is 0. I still am trying to get people to do the alphabet correctly, Will. Okay. So the Z coordinates are 0. Are we cool with that? So if I gave you a list of 5 random coordinates and I said, tell me which ones are on the XY plane, wouldn't you only pick the ones that had the Z coordinate 0? Now, there are 3 standard planes: XY plane, there's an XZ plane, and there is a YZ plane. See if I can draw a version of each one of those. If you wanted to do the XZ plane, wouldn't it be this wall here? I like to think of them as walls. Would you agree it's a vertical wall going along the x-axis? If I gave you the coordinates of all the points who were in the XY plane, you might get, I'll only do a couple of these guys. You might get a guy like this. What is special about all the points? What's special about the coordinates of all the points on the XZ plane?
The YED coordinate is 0.
Oh, no. You know, I grade your tests, Will. I just thought I'd mention this to you. It was funny, so I like it.
When I just write the letter out, you can say it in your brain however you
I'll
like.
say it in my brain, right? You're cool. I like that. It was funny. So can you see that there's a kind of asymmetry going on here? But I mean, like, if all the points in the XY plane, their Z coordinates are 0. All the points in the XZ plane, their Y coordinates are 0. Do you know that's an easy way to tell then if a point is in the X, Y, or Z thing? Now, for completeness sake, I'm doing this one. Can you imagine what this one might look like if we tried to sketch all the points on the XZ plane? And here's my little guy going this way. Would you agree it's this wall here? And what do they have in common? Well, I'm just going to do one of these guys. Don't they have the property that their X coordinates are 0? So if you want to know if a point is on any one of these 3 planes, don't we have a very easy way to do? Don't we actually look at which one of the 3 coordinates is 0? Because that will tell you which of the 3 planes it's in. So let's pretend I have a little question here. P, Q, or R? Which one of those is in the XY plane?
Q.
Which one is in the XY plane?
Q.
Correct. And you can tell that because its Z coordinate is 0. Which one of the two that's left is in the XZ plane?
P.
And can't we tell that it's on the XZ plane because its y coordinate is 0? So since this one has an x coordinate of 0, won't that make it on the YZ plane? Are we good with what an XY plane looks like and how you can tell if one point is on it or not on? Getting nods on that. Okay, so let's look at, and this is all nods, let's look at the x-axis in 3D world. So the x-axis essentially, like I should make them maybe red, make them stand out. Right, that's the x-axis. We're looking for a property that makes it easy to tell if a point is on the x-axis. See, remember that the trick here was if you're on the xz plane, your y coordinate is 0, right? But if you're on the x-axis, what can you tell me about the coordinates of every single point that's on the x-axis?
Both the Y and the final letter of the alphabet
Okay,
coordinates are 0.
okay, correct. So anything that's written in that format is on the x-axis. Does that make sense? So 5,00 and -1,000,000, 00, that will be on the x-axis. If a point has 0, 42, 0, won't those points that look like that be on the y-axis? And won't the ones that go 0, 0, 3 be on the z-axis? Great. Now, if I give you a point and its coordinates are 0, 0, 5, that is on the z-axis. Agreed? Which of these 3 planes is it also on?
Wouldn't it be on 2 planes, both the Y z/z and X z/z?
Right. So because that X is missing, won't that make it on the YZ plane? And because that Y is missing, won't that make it on the XZ plane? So yes. In fact, isn't the Z-axis the intersection of those 2 planes? So that's why there's going to be 2. So if I give you, you know, I'm not doing it because we've got a time issue, but couldn't I say 0, 1, 3, 0, 1, 0 and 52, 0, 0, and you'd get a similar kind of combination, right? You could tell me which axis it's on because there's 2 zeros in the number, but can't you also tell me which 2 planes it's intersecting with? Now, let's look at the closest point to a plane question. So imagine that I have, darn it, I'll try my best, but I don't think I'm going to do a great job at this. There. Can you imagine we've got the XY plane, right? I'm trying to draw the floor, but it's kind of hard because, yeah, whatever. I have a point whose coordinates are 1, 2, 3. And I want to answer this question. The shortest distance to the XY plane. Right, so it's the shortest distance to the floor. What number is that?
Is it 0, 0?
Well, it's a single number I want because it's a distance. Now, I could try and draw it really badly. Can you imagine?
Well,
That's
you're going to want
key.
the shortest line is going to be a straight, or the shortest distance is going to be a straight line. So it's going to be straight down 3 at 1,2.
Correct. You got it all in one go. You answered actually my second question, just go. So the shortest distance will be 3. Just like Tim said, would you agree that if you're floating in midair, isn't the Z coordinate how far off the floor you are? Right. And if you wanted to know the place where it hit the floor, would it be the point 1, 2, 0? I guess I should call that Q. Does that make sense? If I give you the coordinates of a point and I say, what's the shortest distance to insert plane here? Depends on what the plane is. In this case, the shortest distance is 3. What would it be if I took the same point and I wanted the shortest distance to the XZ plane? What would the shortest distance to the XZ plane be for this guy?
2.
Correct. And wouldn't it meet at the point 103? And for completeness sake, which one are X, Y, X, Z, Y, Z? What would the shortest distance of this point be to the YZ plane? Great. And wouldn't it hit at the point? Have you noticed that it's very often the letter that's not mentioned in the question is where the answer comes from? You know, it talks about the XY plane, but wasn't it the Z coordinate that was important for the answer? And you talk about the XZ plane, isn't it the Y coordinate is where all the answers are? And YZ plane, isn't it where the X coordinates value is where all the fun is? Are you beginning? I think some of the engineers have got a big head start on you, but are you beginning to visualize in 3D to try and imagine what these darn things look like? Because that can only take you so far. Don't you physically have to kind of just think of 3D? If it helps you, think of a nice box room and then pick a corner to be the origin. And can you see the floor is your XY plane and one of the side walls is your XZ plane and the other one is your YZ plane. And you're sitting inside or you're living inside the 3D world. So you're trying to visualize where a point is. Think of it as some point floating inside a 3D room. I don't know if that to me, it's an analogy, but it might help some of you to try and get your head wrapped around this 3D world. And we have, God, time flies when you're enjoying yourself. With the exception of Will, who I'm going to, as soon as we leave, drop him from the class, and the rest of you can have a nice day. So say your last name and bye-bye.